Hello everyone. It has been so long since I last streamed. I think it's been 2 weeks. I mean, not that long, but still. So, last time I was doing sequences and series. I finished most of these. I finished, I think, the comparison test. I'm going to revise them and then I'm going to start alternating series. But let's do like a quick review of what I remember. And discrete math. I think I added some topics in the calculus section. Let me just see. Yeah, the integral test. I think it was more appropriate here than in the discrete math section. Anyways, is my avatar lagging? Never mind. So if you have a sequence is like a list of terms. So 2, 3, 4, 5, so on. It could be finite or infinite. But sequence is a list of terms which I think it always follows a pattern. Would you call it a sequence if it doesn't follow a pattern? I think the sequence has to follow a pattern. So also it can be written like this. So this is like term A1, term A2, term A3. All the way till AK. I don't know why I'm lagging so much. Hold on. This is how you represent this. It doesn't have to start from 1 and it can go all the way till infinity as well. Now, there are two special types of sequences. One is the arithmetic sequence. So it's like there's a term, let's say 3, and then the next term is 3 plus some constant number. So let's say 3 plus 4, 7. And then the next term would have plus 4 again, 11. And then 15. So plus 4 plus 4 plus 4, 19, and so on. Could either be infinite or finite. And we represent in each term, let's say this is n is equal to 1, another this is n is 2, n is 3, n is 4, and so on. You can represent it like this. A1 is the first term, and the second term A2 would be, instead of writing this, I can rewrite it like this. A1 plus A difference. So plus 4 in this case. Then the next term could be written as plus 2D. So plus 4 plus 4. And then the next one would be written as 3D and so on. So for a particular term, an, it would be equal to the first term plus n minus 1d. Oops. This is the formula for a particular term in a sequence. And if it follows this pattern where a constant is being added, then it's called an arithmetic sequence. Similar to sequence, we also have series. But let me represent another sequence, then I will go to series. So the next one is geometric sequence, where there's a ratio constant be a constant ratio being multiplied. So a1, and then you have a1 times r, and then a1 times r again. So the previous term times r, and then a1 r cubed. Of course, this follows a pattern of an a1 r to the power of n minus 1. I'm waiting for this to be loaded. Anyways, so an example of this would be 2, then r could be 3, so 2 times 3 is 6, and then 6 times 3 is 18, and then times 3 again. I'm using a calculator. Times 3 again, 162, and so on. Hold on. Just trying to open Desmos. So anyways, we have a geometric sequence where a term is represented like this. We have an arithmetic sequence where a term is represented like this. Like sequences, we also have series where each number is being added. Okay, let me do. So in a series, we have a1 plus a2. The terms are basically being added, plus a3 and plus a. Okay. So a series is represented like this. Or I think I. Sometimes they use I. Never mind. So in arithmetic sequence, arithmetic series would be like this. A1 plus it with A1 plus D, and then plus that with A1 plus 2D. So if this series goes to infinity, then the total sum, let's call it S would go to infinity. So an arithmetic series would only exist if the terms are finite. But we can calculate instead of adding them all one by one, we can calculate the series by a simple formula. So I can also represent S in reverse. So A plus n minus 1D. So this is the last term. And then this is the second last term. And then this is the second term. And then this is the first term. If I add all of them together, I get 2s is equal to, for the first one I have 2 times the first term plus it with n minus 1d. For the second one, I also have 2 plus the first term, and then d plus 2 n minus 2d, which is n minus 1d. So this and this makes this. Also, you may notice that these two look exactly the same. For the third one, it will also be 2a1 and then plus 3d plus it with n minus 2d, which will give n minus 1d. So basically, when we are adding them, this plus this, this plus this, this plus this, and so on, we get the same value being added a particular number of times. But this makes sense because a1 is being added twice in each term. And then since the first, we are adding the first and last. Wait, hold on. Yeah, we are adding the first and last one. It's always going to be n minus 1d. If we go to the next term, let's call over here, a 1d gets subtracted. Over here, 1d gets added. So the sum is basically the same. So we can represent this as, since there are n terms in total, we can write d, and then s is equal to n over 2. N minus 1 d. Now let's just check. Finding a term in an arithmetic sum of an arithmetic series. Yeah, this is what we got. Now let's do a series for a geometric one. Geometric series. Last time I said an arithmetic series has to come to an end. Otherwise, if it goes to infinity, the sum would go to infinity, even if it's like 0.001. But geometric series is different. We have S. We have A1. Let's say the geometric series is, let's say the geometric sequence is like is equal to, particular term is equal to no, that doesn't reach us anywhere. Basically, let's say the sequence is this. You have 1 and then divided by 10. So the ratio is 1 over 10. And then 1 over 10 again. And 1 over 10 again. And so on all the way till infinity. If we add them all up, What do we get? This goes all the way to infinity, so this is equal to, you have 1 point plus 1 1 1 1. Do you guys understand how I got this? So it's a 1 plus 0.1, which gives 1.1, and then plus 0.01, which gives this 1.11, and so on. Basically, what I'm saying is, for a geometric series, even if the series goes to infinity, you can still get a finite number. Now, this only works if r is between -1 and 1. So a1 plus a1r. If r is between -1 and 1, then this term would be smaller than, like, the absolute value of this term would be smaller than the previous one. R square this gives s. Oops, let's say this goes to infinity and we get s. The sum goes to infinity, and then if we have rs, then it's a1 r plus a1 r squared plus cubed and so on. Well, let's assume the series is finite. No, wait, this is -1. And then we can, this and this are same, this and this are same, this and this are same, except for a1 and a1rn. Every term is being repeated in both s and rs. So we can do s minus rs. This and this would cancel out, this and this will cancel out, and we would be left with a1 minus a1 rn. And then so the sum is the first term times it by 1 minus r to the power of n over 1 over r. Now, if this goes, n goes to infinity, then we have this. First term divided by 1 minus r. If n goes to infinity and r is between -1 and 1 only in this condition, then this will go towards 0. And then a1 times 1 is a1. So this is the formula we get for the sum of a geometric series. So we learned about sequences. This is how we present it. There's a formula way and then there's a curly bracket way. So there's a curly bracket way, and then there's a formula way to present it. Also, there's a recursive way where you're defining a in terms with respect to the previous term. So for an arithmetic series, sorry, for an arithmetic sequence, a recursive one would be like this, defining the next term in terms of the previous term. And then for a geometric one, it would be like this. The previous term times r. So what does it here say? A sequence an converges to a real number L if for all epsilon more than 0 there exists an integer n such that n minus L is less than epsilon if n is greater than or equal to n. Okay, they're talking about the convergence. Also, there's a special series called a harmonic series. It's like 1 plus plus this series. It looks like it converges, but it doesn't converge. So we can prove it like okay, we can prove it like this. Let's say this is h1, this is h2. So what I will do is I'll turn this one into half. I'll turn this one into 1 over 4. So basically half plus 1 over 4 plus 1 over 6 basically what I'm doing is I'm taking all the odd terms and making it equal to the next term. So this one, instead of writing 1, I will write half. Instead of writing 1 over 3, I will write 1 over 4. Instead of 1 over 5, I'll write 1 over 6. And these odd terms, so basically 1 is more than half. 1 over 3 is more than 1 over 4. 1 over 5 is more than 1 over 6. This is the same for all odd terms. Basically, h1 is more than h2. However, if you look closely at h2, we can add all of this and see what we get. h2 is equal to 1. 1 over 4 plus 1 over 4 is 2 over 4, which is half. 1 over 6 over 1 over 6 is 2 over 6, which is 1 over 3. Then same, it's 1 over 4. 1 over 5. So on. So now we conclude is equal to h2. But there's a contradiction here. So no such limit or no such sum h1 or h2 exist, because then it will cause a contradiction. limit of a sequence defined by a function. Hold on, what's this? Okay, first of all, let's try to understand this. Given a sequence, I already read this, but I'm doing a revision. If the term a n become arbitrarily close to a finite number L, as n becomes sufficiently large, we say a n is a convergent series, and L is the limit of a sequence. In this case, we say the sequence is a convergent sequence. If a sequence is not converged, it is a divergent sequence. But there's a test for convergence, right? I think we will get there later. Consider a sequence an such that an is equal to f of n for all n greater than 1. Does it have to be 1? There exists a real number L such that, I think they should say if there exists a real number n and an integer capital N such that for all n greater than equal to capital L, there exists a limit, then an converges. So they're finding a function such that each term of the sequence is equal to that function. I think there are better concepts of convergence later on. Bounded above, bounded below. So bounded above and bounded below would be like, this is the sequence. X-axis is basically the n. Then AF1, AF2, AF3, AF4 and so on. Let's say it goes like this. So basically it doesn't go above this line and it doesn't go below this line. Then the sequence is bounded below this line and bounded above by this line. I think the next chapter is about infinite series. I'm still doing a revision. Did I write about the divergence test? Did I write it here? No, I wrote the integral test, but not the divergent test. Okay, this, if it doesn't go to infinity, we say, if it's a finite series, we say it's a partial sum of the infinite series. And then they're talking about the harmonic series, algebraic properties. So what part do I need to revise? Oh yeah, telescoping series. Basically, over here, we did this. A1, these two subtract, these two subtract, these two subtract, and then we are left with two terms. If we have something like this, then it's called a telescoping series. Well, this isn't a telescoping series, but telescoping series is like the subtraction and addition is part of the series. I guess by using partial fractions. Oh yeah, so they want to check if this series converges or not. They rewrote this into this 1 over n minus 1 over n plus 1, and then they're summing this. But then they're left with 1 minus half, and then half minus 1 over 3, and then 1 over 3 minus 1 over 4. But the thing is, the half and half cancel out, 1 over 3 cancel out, 1 over 4 cancel out, and so on. So you're just left with 1. Since it goes to infinity, only 1 remains. Where did it go? Yeah. Writing out the first several terms in a sequence of partial sums, we see that, oh, they're doing partial sum. S1 is 1 minus half, S2 is 1 minus 1 over 3, S3 is 1 minus 1 over 4. In general, for the partial sum, so 1 minus 1 over k plus 1. A telescoping series is a series in which most of the terms cancel in each of the partial sum, leaving only some of the first and some of the last terms. So, in a telescoping series is like infinity, n is equal to 1, b, n. Do they use n or do they use I? Alright. So the first term minus the next term, if we sum it, the second term, so b2 minus b2 will cancel out with plus b2 in the next term. So we are left with b n minus it with whatever it converges to. Whatever this is. That's the capital B here. Divergence and integral test. What is this? What is this? Okay, I need to change this. Anyways, basically for the integral test, uh, if we have this infinity n plus 1, and n I plus would be greater than for all I. So basically, in the entire series, the next term will be smaller than the previous term. So it will go something like this. Let's say the series has a limit over here. Basically, what the integral test says. Suppose there's a function called f of x where f of n, so where basically f of n is equal to a of n after some point. Let's say there's a point C such that if n is greater than or equal to C, these start becoming equal. So f of n would, for example, be like, for example, this is the function, right? And then from 2 point onwards, from this point onwards, f of n is equal to a of n. So basically we can do an integral test over here where, let me change the color. We can use the left Riemann-Sum and right Riemann-Sum with intervals of, let's say here we have, let's do 3, 3, 4, 5, 6, 7. So the right Riemann-Sum would be a triangle going all the way up till here. Actually, this here, this. We are using intervals of 1. And what we are trying to figure out is actually let's do from A4 onwards. So this area over here, this area over here is A4. So A4 times 1, basically A4. This area over here is A5. This area over here is A6. This area over here is A7, and so on and so on. So the integral from 3 to infinity or let's do k actually would be from A4 plus A5 plus A6 plus A7 till AK. Yeah. Is that correct? Yeah, that makes sense, I guess. So A7 would be the last. Then you're finding the integral from 3 till k, and then AK would be last, and it starts from A4. Now we are going to use the left Riemann sum. We are going to do this, and then here, 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 this included from 3. So the area of this is A3 because it's 3 times 1, A3 times 1, A4, A5, A6. And then 8. So before we concluded this, we can also say K4. So A4 plus A5 plus A6. This gives the area from 4 to 7. Or we can say from 4 to K plus 1. Right? So area from so integral from this till 7. Sorry, not hold on. What am I doing? It's not this. It's the left. Well, here's the right Riemann sum, so this sum would be less. Would be like this. So you have the area under the graph, and then the sum of the squares would be an underestimate. Over here, the sum of the rectangles would be an overestimate. So this would be an overestimate from 4 to k. Let's say, for example, from 4 to 7, the overestimate would be A4, A5, A6. So A4, A5, A6. If we do it till k, AK, then it would be an overestimate from 4 to k plus 1. Basically, what I gathered is this. And This is n. Um, this is called the integral test. This is k plus 1. Sorry, this is 3. Or you know what? We can write it like this. Normally, when we are writing comparison, we write the lowest one first. From 4 to k1. And then um, hmm, for this one, we can start it from 4 and then we can add a4 separately. So what I mean is, instead of from 3, we can do 4. So this is an underestimate of this area from 3 to 7, a4, a5, a6, a7. But we can add a4 separately and we can add a5, we can do the integral from 4 to k, then add a4 separately, which is what I'm doing here. You can generalize this. So let's say the starting number is, what do you want the starting number to be? What did they write it in the book? They have gone past it. Let's say the starting number is I. Or let's say the starting number is X. The assumption is that f of f is continuously decreasing and it matches with, it is equal to every value of a after a certain point, such that this works. Like from x onwards, f of n and is equal to a of n. F of n is equal to an. Then this formula works. That is the integral test. I use capital N here. So this is wrong. Shouldn't it be a n? It should be a capital N. And so there's a mistake here and a mistake here which I need to fix. What else was there? Oh yeah, the divergent test is basically if the sequence A1, A2, A3 and so on, if this is not converging, then their series will not converge either. And if this is converging, then the series is inconclusive. It may converge or it may not converge. A harmonic series is an example of this. It looks like it converges because each term approaches zero, but it doesn't converge. Let's go down. P series. Okay. P series. P series is any sum that is written like this. I think. Yeah. So the harmonic series is a P series. Another P series is 1 plus 1 over 2 square plus 1 over 3 square. And so on. Of course, this could be a negative as well, in which case this is also a P series. If it's like negative 2 instead of 2, then the number would go into the numerator. P equals minus 2. Well, I guess it's trivial that if it's negative, then of course the series is divergent. If it's negative, then the series is divergent. If it's 0, then you have 1 plus 1 plus 1 plus 1, which is still divergent, and the harmonic series is divergent. So, if P is less than or equal to 1, then P series is divergent. And they use the integral test over here. Wait, for we have integral of, I'm just testing something. 1 over x dx. We would have ln of x, right? Ln of, but this is all the way to infinity. ln of infinity minus ln of 1. Yes, ln of infinity is infinity. If the area approaches infinity, like if we have a case like this where the function is matching the sequence and the area of the function after a particular point is reaching to infinity, then the sum of the sequence would also go to infinity. But if you have something like infinity 1 x to the power of p is equal to, this is x to the power of minus p, so this becomes minus p plus 1, which is like this over this, right? So the derivative of this would be x to the power of minus p, yeah. And then what? P is greater than or equal to 2. So this would be in the denominator. And then infinity of this would be 0. So 0 minus 1 over 1 minus p, which is equal to 1 over p minus 1. P is more than 1, then P series converges to 1 over p minus 1. Does the P series start from 1? Okay, I guess so. The remainder estimate confuses me. So we have, let Sn be the nth partial sum of the series of A of n. Then we have this. I don't understand. Okay, this part confuses me a little. Suppose a and there exists a function continuous decreasing. Okay, I understand this. If I from here we subtract Sn from both sides, so the sum minus the partial sum is the remaining sum. I get that. Did I write it here? No, I did not. I think this is the same thing as Riemann left sum and right sum. You're using n plus 1 here. Oh yeah, I guess that would make sense. If this is the sum, then the rest of the sum would be, let's say this is the partial sum from till k, then the rest of the sum will be from k plus 1 till infinity, and over here from k to infinity. Okay, what's next? Comparison test. We are still on revision, by the way. Suppose there exists an integer n such that 0 is less than n, which is less than Pn for all n greater than or equal to capital N. If okay, I think that makes sense. So you have one partial sum here, another partial sum here. If this top one converges, the bottom one will converge as well. And in this example, we have this and this. If the bottom one diverges, then the top one will also diverge. This is assuming that this sequence will always be greater than this sequence, or there's a particular point at which this sequence is greater than this sequence. Same thing here, there's a particular point at which this sequence is smaller than this sequence. So if the top one converges, the bottom one will also have to converge. But my question is, hold on. The thing is, the bottom one might not converge to 0. It might go to negative and all the way down and still be less than the top one. This I understand. This I'm a little confused. Because it's not necessary the AN might converge. It could be AN goes. Oh no, wait, it says AN is more than 0. Yeah. Do they mean BN converges to 0? If BN converges to 0, then AN will just squeeze in between and also converge to 0. Limit comparison test. If limit of AN over PN is an actual limit which is not 0, then either they both converge or both diverge. Okay, so for let's say this is equal to L, which is not 0. If this reaches a particular constant, then if this diverges, if either one of them diverges, then the other one also has to diverge. Okay, let's see. Let's think about this. If Bn diverges, if Bn diverges, then the entire thing is going towards infinity. If Bn diverges, but An has to converge, right? Otherwise, if Bn or and An both diverge, they may not go to infinity. So if Bn diverges and An converges, then limit goes to infinity. Hold on, no, let me. I mean, it's correct, but let me put this another way. If limit goes to infinity, and if the limit is going to infinity and Bn is converging and Bn converges, sorry, Bn diverges to negative infinity or to infinity, then an shouldn't converge. An also has to diverge. Otherwise, the limit would be a particular value. Then an has to converge. If we find that the limit goes to infinity and Bn is diverging, then if an converges, it doesn't make sense that the limit is going to infinity. If Bn diverges and an converges, then the limit is going to a particular value, right? Then this has to be like this. If the limit goes to infinity, the limit is infinity, and if Bn diverges, then An also diverges. It doesn't make sense for An to converge, otherwise the limit would reach a particular value. If limit is 0 and if An converges to 0, nope. Yeah, I think An converges to 0, then Bn also converges to no, that doesn't make sense. Yeah, let me see if I'm right. Let's see. If Bn converges to a particular value, if Bn converges, then An also converges. An cannot diverge. Converges, then An also converges. An cannot diverge. If it diverges, then the entire limit would go to infinity, but we already said that the limit is 0. If limit is L, which is not 0, and if then if limit goes to a particular value, then you cannot have the case where one converges and the other diverges. If this converge and this diverges, then the limit goes to 0, right? I think. Yeah. I don't know why I'm getting so confused. If this diverges and this converges, the limit goes to infinity. So either both N and Bn converge or both diverge. Yes, finally. I'm caught up. Well, I'm almost caught up because I was confused a lot during the revision. The alternating series test. A series whose term alternate between positive and negative values is an alternating series. For example, the series 1 over 2 plus 1 over 4 minus 1 over 8 plus 1 over 16. And this one are both alternating. Series 1 in equation 5.11 is a geometric series where r is minus half. So the series converges. Right. Series 2 shown in figure 5.12, which is 1 minus half plus 1 over 3 minus quarter, is called an alternating harmonic series. We will show that whereas harmonic series diverges, the alternating harmonic series converges. Consider wait, let me think. I can do this. We can put all the even values on one side and the odd values on the other. So odd. 5, 6, 7. But I don't know if this sends us anywhere. Plus 6. So this is a geometric series where r is just half. No, this is not a geometric series. But the thing is, if I extract half out, I can get like something similar to a harmonic series. So I have 1 plus half plus 1 over 3 plus 1 over 4. The harmonic series diverges. What are they doing here? I have no idea what they did. S2k plus 1 for k more than 0. So you have the previous term minus half plus, consider the odd terms. Oh, this is the next odd term and previous odd term. Hold on. So 1. The odd ones are all minuses. We consider the odd one and then the previous odd one. So is this sum to odd one? Consider the odd terms. Sequence of 1. No. So S of n is a particular term, not a partial sum. Right, so this is 2k minus 1 and S2k plus 1. This is S of 1, this is S of 3. So basically, considering take an even number, take an even term, and consider the odd term before and odd term after it. So either 1 and 1 over 3 or 1 over 3 and 1 over 5 or 1 over 5, 1 over 7 and so on. The odd term is sorry, wait. The next odd term is S2k plus 1. K here is what? K here is sk. So this is k is 1, k is 2, k. I'll put k here. And I'll put s of k here. So 2k 4. 2 times 2 is 4. 3. I don't understand what's happening. Minus 2k plus 2k plus 1 over 2k plus 1. One over 2k minus 1 minus 2k plus 1 over 2k plus 1. I get that it's a decreasing sequence. Two, four, 6. So 2k is one of these. Let's take 4, 2k, let's take 4 minus 1 and plus 1. So minus 1 over 4 is lesser than both of these. Since it's a decreasing sequence, it's lesser than 1 over 3 and it's lesser than 1 over 4. 3k minus 1 minus 1 over 2k. That doesn't make any sense. This does not make sense to me. This is equal to this minus 1 over 4 plus 1 over 5. That does not make any sense. Wait, no. I think 1 over 3. K is half. Minus half plus 1 over 2k plus 1. an alternating series of the form minus 1 to the power of n plus 1 bn or minus 1 to the power of n bn converges if 0 bn. So it's decreasing. Limit bn is equal to 0. Okay, yeah, that makes sense. Basically, the series converges if the absolute value of term is like lesser and lesser. So it's like series is like this, 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 this. The absolute value is lesser. The absolute value is like this, 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 this. And it also converges to 0. So limit bn to infinity is 0. I'm still confused by what they're doing here. For each of the following alternate series, determine whether the series converges or diverges. So it is decreasing, and 1 over n square goes to 0 when n goes to infinity. As for this one, I don't think it converges because is it decreasing? 3 over 4, 4 over 5. Okay, it's not decreasing, so no, it doesn't converge. It is difficult to explicitly calculate the sum of most alternating series, so typically the sum is approximated by using partial sums. When doing so, we are interested in the amount of error in our approximation. Consider the alternating series Bn satisfying the hypotheses of the alternating series test. Let S denote the sum of the series and Sk be the corresponding sequence of a partial sum. Rn S minus Sn is less than or equal to remainders in alternating series. Let S denote the sum of the series and Sn denote the nth partial sum for any integer n greater than n by remainder. The remainder Rn, which is equal to S minus Sn, satisfies this. Why would the remainder of the sum be less than or be equal to bn plus 1? From what I understand, what they're saying is we have an alternating series like this. We calculated sum of the sums. We want to calculate the remainder. So we do, we calculate it till here. This is n, n, and this is capital N, which is this, and this is n plus 1. The remainder of the sum is equal to b n plus 1. That's what I don't understand. Why would the remainder sum be equal to b n plus 1? This makes more sense. The absolute value of the remainder of the sum is less than the remainder of the sum starts with b n plus 1, right? To determine a bound on the error R10, if you approximate the sum of the series by the partial sum S10. So we have calculated n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have summed them. We want to calculate from 11 onwards. Why would it be like this? B11. So the total sum minus what we have calculated till here. Now we haven't added this. So these I'll have to check when I'm alone. A series exhibits absolute convergence if an converges, if the absolute value converges. Series an exhibits conditional convergence if an converges but the absolute value diverges. Absolute convergence, if the modulus converges, then an converges. Okay, this I can understand. The sum. Yeah, actually I can understand this. Determine whether the series converges absolutely or converges conditionally or diverges. This is an alternating series. 1 over 3 n plus 1. If n goes to infinity, it diverges, right? No, it converges. 1 over 3 n plus 1 will converge when n goes to infinity. But I think even the absolute value will converge. The absolute value converges, then this converges. Here the absolute value. 1, 2, 3. Compare this. 1 over n square. So cos n will be less than or equal to negative 1. 1 over n square converges by the comparison test. Yeah, what do you mean by the comparison test? This also converges. The modulus converges, then the main function converges. What do they mean by like the integral test? Oh, you mean wait. I know what they're talking about. The an over bn thingy. This. If limit is 0, bn converges, then an also converges. The value of cos n is going to go all over the place, right? But 1 over n square will converge to 0. I think that makes sense then. Yeah, I need to check this. Or maybe in someone in the comment can help me. Okay, ratio test. Let A and B a series with non-zero terms and let, is this row? I could just call it P. P is equal to limit n to infinity, the absolute value of a n plus 1 over a n. If P is between 0 and 1, then a n converges absolutely. If rho is more than 1 or infinity, then an diverges. If rho is equal to 1, the test does not provide any information. Let an be a series with non-zero terms. We begin a proof of part I is less than 1 since p is between 0 and 1. Then there exist R such that it I think from intuitively, let's think about this. For if n goes to infinity and rho is between 0 and 1, n converges. Why can it not? What if it diverges? Still thinking. There exist. Okay, since p is between 0 and 1, there exist R such that uh, p is between 0 and R. Okay, let epsilon be equal to R minus p, which is more than 0. By definition of limit of a sequence, there exists some integer n such that n minus n plus 1 over an minus p is less than epsilon for all n greater than n. By definition, this is between 0 and 1, right? And then therefore an plus 1 over an is less than p plus epsilon, which is equal to r. That, okay, thus we have this an plus 1 is equal to r an. Then we have r squared here, r cubed here. Okay, since r is less than 1, the geometric series converges. Given the inequality above, we can apply the comparison test and conclude a n plus 1, a n plus 2, a n plus 3, a n plus 4 also converges. Therefore, since sum an is equal to partial sum plus the rest of the sum, the partial sum is a finite sum, then and the infinite one converges, we conclude that all of it converges. Yeah, I don't understand anything. I'll try to understand this in my spare time. For each of the following series, use the ratio test to determine whether the series converges or diverges. 2 to the power of n over n factorial. So plus 1 is 2 to the power of n plus 1, which is 2 to the power of n times 2. And then I can do this. And then, oops, 2 to the power of n. Wait, hold on. It's not, made a mistake. It's n factorial. N plus 1 factorial. And this is times 2. So you have like that. I hope I'm right. These two cancel, n factorial and n factorial cancel. We are left with 2 over n plus 1. And then 0 because this keeps growing bigger and bigger. So it converges. The series converges. What about this one? N to the power of n. Let me think about this. And then this. And then we are left with this. Then what happens if this goes to infinity? N goes to infinity. Hmm. Let me think. This is multiplying n times. Wait, hold on. No, I thought I was... This looks familiar. Is this equal to E? If this is equal to E, then the series diverges. Yeah, then the series diverges. N factorial squared over 2n factorial. This looks like an exponent. I got this. And then 2n plus 2 factorial. Now let me think. One factorial 2n plus 2 factorial. This would be reversed. So we have 2n factorial and this n factorial squared. I think this would give us n plus 1 squared. N plus 1 factorial divided by n factorial is n plus 1. Since both of them are squared, I guess n plus 1 would also be squared. This is plus 2, right? 2n plus 2 factorial would be 2n plus 2 times 2n plus 1 times 2n and then so on. And this would become 2n plus 1 factorial. As limit goes to infinity, this would increase faster than this. Right? This factorial increase faster than square. Oh wait, it's not factorial. What am I doing? It's this. I can extract 2 from here. So then I'm just left with I can extract 2 from here, and then I'll be left with n plus 1, which can cancel out with this, and or here as n goes to infinity, I'm left with half, which is wrong. Wait, hold on, how is it half? If I extract 2 from here, okay, I will divide both sides by n. Yeah, it's actually 1 over 4. Root test. If it's like this, then p is between 0 and 1, then an converges absolutely. If it's more than 1, then an diverges. P is equal to 1, then the test does not provide any information. Excellent. I need more proof. Like if someone has a good proof for the ratio test and root test, be great. Is the next chapter about the Taylor series? Because I really wanted to learn that one. Review exercises. What is this? Yeah, it's the power series. Yeah, this is what I will start doing next stream. If it loads, that is. Anyways, guess I'll end my stream here. It wasn't. But actually, I did not enjoy the last subject. I don't know why. I like the review more. But the proof, if the proof isn't very clear to me, then it bothers me. Yeah, but end the stream here, and then next stream I would start with the Taylor series. Okay, I guess I'll see you then.